Hello guys, welcome on Tesla Adventures. In this video, we will be discussing the capillary action and the capillary rise. So, first of all, let me tell you that what is the capillary action in day-to-day life. You must have seen that the plants transfer the water from roots to leaves, and this transfer is done against the gravity. So, this is due to the fact that the cohesive force of the atoms or molecules of roots is pulling, in fact, the adhesive force of the atoms of roots is pulling the atoms of the water against the cohesive force of the water molecules and against the gravity also. So this is the capillary action, capillary rise, and I'll give you another example in which you must have seen if you imagine Indian houses on Diwali, then we used to light up the diyas, and in diya we always fill the diya with oil or ghee, and there is a bati, which is a cotton thread, thick thread, which is burning on the top, and its tail is inside this oil or ghee, and you will see that eventually all this ghee or oil will get finished, and it will be burning at the top. So this rise of this ghee or oil from the tail to the top is also due to the capillary action, or this is the same capillary action is the same concept on which the laltans, which laltrons, which Indian villages still uses for uh, light purposes in the night. So this is the capillary action or capillary rise. Now, if we talk about the capillary tube, so let me explain that capillary tube is a narrow tube which is made up of glass, and you must have seen the burette or pipette or a test tube in your lab. So the capillary tube is of that thickness. If we talk about the thickness of pipette, so the thickness of capillary tube is almost the same as the thickness of the pipette, and capillary tube is open from both the ends. So it is a narrow tube which is open from both the ends, and it is made up of glass. Now, meniscus is defined as the shape of free surface of liquid inside the capillary. So, this we have already discussed in previous videos. You can find these videos in the playlist. And let me tell you again that in the experiment of volumetric titrations you must have done, you must have taken use of burette and pipette. So the reading in the burette was taken with the lower meniscus scale. At this point, reading was taken. So this is the meniscus. Actually, when you fill some liquid in burette or pipette or test tube, then the liquid shape becomes curved, or sometimes it is flatter also. So that shape of the free surface of the liquid is called as meniscus. And as we have already discussed, the upper, lower, and flat meniscus in the previous video. Now, again, the capillary action is a phenomena of rise of liquid against the gravity due to dominance of adhesive force over the cohesive force. Now, let us discuss in this video about the height to which this liquid will rise inside this glass capillary when dipped into the liquid tube, liquid tank. So this liquid will rise in this tube, and this is the shape of the meniscus, and it is called as lower meniscus. And if we draw the complete sphere, then this will be the radius of this sphere, which is the sphere of which this meniscus is a part of. So this is the radius of the meniscus curvature, and this is the radius of the tube. Now we have already discussed the angle of contact in detail in previous videos, and therefore we can directly refer it here. So this is theta, and this is also theta. So we can say that small r cos theta is capital R. So small r is equal to capital R upon cos theta, first of all, where small r is the radius of the meniscus and capital R is the radius of the tube, and theta is the angle of contact. Now let us discuss that why this rise of liquid occurs, or in this case we are talking about the rise. So let us name the points A, this is B, this is C, and this is D. Now point A is just above this free surface, or we can say that it is just above the free surface and on the concave side, while B is just below the free surface and on the convex side, while C is just at this interface inside the tube below the B, and D is outside the tube on the interface. So these are the 4 points. Now, if we talk about the pressure at A, so the pressure at A will be equal to P naught, because A is exposed directly to the atmosphere. So the pressure at A will be equal to P naught. And we also know that we have already studied in the video of excess pressure that due to this curvature there is a pressure difference that occurs between the concave and convex side, and the concave side is at the higher pressure. So the pressure at A is greater than the pressure at B by the amount of excess pressure, and the pressure of A is definitely equal to P naught. So we can say that pressure at B will be less than pressure at A, and it would be less by excess pressure, which is 2T by R. Now, we have already discussed that in the case of spherical liquid surface, the excess pressure is either 2T by R or 4T by R. In this case, we'll be taking 2T by R because the free surface is only one. There is air only above this meniscus, and below this meniscus is the water. So there is only free surface, only one free surface of this meniscus. Therefore, the excess pressure will be 2T by R. Okay, now at point C, if we talk about pressure at point C, then it would be the sum of pressure at B plus H rho G. And this can be written as P naught minus 2T by R plus H rho G. Okay, and the pressure at C will be equal to pressure at D. And D is also directly exposed to the atmosphere. Therefore, the pressure at D will be equal to P naught. So this is P naught minus 2T by R plus H rho G is equal to P naught. And cancelling this P naught with P naught, H rho G is equal to 2T by R. This is the fact that this liquid rises inside the liquid. See, actually, if H is 0, then there is no difference of pressure to counterbalance this excess pressure. So if H is 0, 2T by R is 0, then it is not possible. R should be infinity in that case, and that is the case of flatter meniscus. So to counterbalance this excess pressure developed due to the curved meniscus, this liquid rises or depresses. I'll be discussing that depression in the liquid in this video in the later part. So H is this one, and for obvious reasons we cannot measure the meniscus radius. So we have already replaced this radius with R upon cos theta, where R is the tube radius and cos theta. Theta is the angle of contact, which is definitely a constant value for a fixed pair of liquid and solid. So H will be equal to 2T by R rho G into cos theta. This is the value of height to which this liquid will rise. Now, if we discuss another method, see, This method helps you in understanding the fact that why this liquid rises or depresses, and the second method helps you in solving the complex questions of capillary action. I'll be discussing those questions in the later part of the playlist. And in this method, you can imagine, we will be applying some mechanics in this method. So you can imagine that if we talk about the top view of the tube, if we are visualizing this from here top, this is the top view, and from the top you will be watching the liquid filled in the tube, and there will be infinite contact points of the liquid with the tube, and the radius of this liquid of the radius of the tube will be r. So the force, adhesive force, which would be pulling this liquid will be like this. This will be the adhesive force, F adhesive, and this will be the angle of contact, theta, theta. This will be theta. This will be theta, and F adhesive will be equal to, now I'll write down, yeah, F adhesive will be equal to F cohesive, and it would be equal to F. Let's suppose it is F, and this component of F, which is F cos theta. See, I will not take 2F cos theta because these are not just 2 points. These are infinite points. These points are the contact points of meniscus with the tube, and there are infinite contact points. So I'll be taking the F as the total force. So just F cos theta will be lifting the mg of this part, and this m can be written as pi r square h into rho. See, I have assumed that it is almost cylindrical part, and I have ignored this small volume on the edges. So this you can imagine just as cylinder, and F cos theta. Now F will be the total surface tension force, which will be equal to surface tension T into the length of this circumference. Its length is 2 pi r, and this is cos theta, and m is pi r square h rho, and this is g. Cancelling pi with pi, r with r, h you can see will be 2t cos theta by r rho g. This is the value of height, capillary rise, and we have already derived this again. So the second method will be helpful in solving the complex numericals. Now, in this, we can see that in the case of pure, in fact, normal water plus glass capillary. In this case, we know that theta is acute, theta is less than 90, so H will be positive. So if a normal water is filled in a glass capillary, then definitely it will rise. And in the case of distilled water, if we talk about the distilled water plus glass capillary, this is glass capillary, then we know that theta is 90 degree and h is 0. This is the flat meniscus, and it will not rise because we have already discussed that this rise or depression occurs due to the curved nature of the free surface. If the free surface is not curved, it is flat, then it would definitely not rise or depress. Now if we talk about Hg plus glass capillary, this is mercury and glass capillary, then we have already discussed that for Hg and glass capillary, the angle of contact is greater than 90. It is obtuse, and cos theta at the obtuse angles is negative. So H will be negative, which means that mercury will depress down below the outer level of the liquid inside the capillary, and this phenomena is obviously due to the fact that cohesive force inside the mercury molecules is very, very greater than the adhesive force that glass applies on the mercury molecules. So guys, that's it in this video, and in the next video we'll be discussing some more important concepts which are related to this capillary rise. Thank you.